Good afternoon, everyone. My name is Martinette Aguilar. I am a senior ocean engineering student here at the University of Southern Mississippi. And I'm going to be presenting to you guys today my senior capstone project, which is a proof of concept wave flume. So just to give you guys a little background about my project, in the beginning of this class, I did want to create a wave energy converter, mainly an oscillating water column wave energy converter. And an oscillating water column wave energy converter works, it uses the heaving motion of the wave, which it has like this air chamber right here, and it has like this turbine, and as the wave goes up and down, it generates like an air, which in turn turns this turbine, and there's going to be like an energy converter inside this turbine, and basically turns its motion into energy. But to accomplish this project, I would need to create this chamber wave energy converter with a wave flume. So that's like two projects at the same time. And I don't think that a 2-semester deadline is a sufficient time to be able to achieve this project. So in turn, I had to focus into just creating the wave flume. So a wave flume is like a specialized tool that scientists and researchers use to test products like buoys, like wave energy converters, and test them in like different wave scenarios inside the lab. Also, another motivation for this project, it is a compact proof of concept project. So if a future ocean engineering student would like to take interest in it and would like to scale it up, they can use the background like stuff that I did and like do it for their project. So diving into the project itself, before we can start anything, we do have to define what type of wave we want to generate. So there's two most common types of waves, namely the shallow water waves, which are waves that has a wavelength that is greater than 20 times the depth. And then there's also deep water waves, which are waves that has a wavelength that is less than double the depth of the ocean. So the main difference of these two waves is that the deep water wave does not have that interaction with the ocean bottom, while for shallow water, it has that interaction with the ocean bottom. In turn, the orbital velocities of shallow water wave are more ellipsoid since they have that vertical limitation. In connection to these types of waves, there is like a specific wave generator that is used to generate these waves. So one is a flap type wave generator. It is more suitable for generating deep water waves because as you can see in this picture, most of the motion happens at the top. So it creates that variation of velocity as you go down, and there's no movement at the bottom. So that's why it's more suitable for generating deep water wave. In contrast, we have the piston wave generator, which is more suitable for generating shallow water wave since it has that interaction with the bottom and it pushes the whole water column. So now that we know the types of waves, the types of generator that it associates with, now we have to know how can we relate the generator into generating the waves that we want. So this is where the linear wave maker theory comes in. And according to this theory, the water displaced by the wave maker should be equal to the crest volume of the propagating waveform. So in this photo, you can see that it basically suggests that the amount of volume that is displaced during this motion is equal to this crest right here. And so in this theory, it gives us an equation of like a ratio of our wave height over like the stroke length is equal to the wave number times the water depth in a flume all over like divided by 2. Since this is a shallow water wave maker theory, scientists derived from this theory and have this equation right here for arbitrary water depth, which is a much more longer and complicated formula. So since this project started as like a wave energy converter project, and in the beginning of this project as well, it was tied into one of my classmates' project idea, and his idea was a wave energy converter as well. And for his wave energy converter, most of like the wave energy converters are located in like deeper waters, since like for aesthetic purposes really they put it in deeper waters because for public, I wouldn't think they would like it or appreciate it if they would see like blobs of like, wave energy converters just in the ocean while like they're swimming in it. Like me personally, I would love to see like the serenity of like the ocean or like the beach. So in return, most of like wave energy converters are located in deeper waters, and in that sense, if we want to if since my project was tied into this project, we wanted to generate deep water waves. So we had to do like a deep water wave calculation, and in this calculation we used the relationship between the depth against the wavelength. So for a wave to be considered as a deep water, the ratio between depth against the wavelength should be greater than or equal to 0.5, and this project has a budget limitation, so we want to create it as compact as possible. So we gave it a depth limitation of 1 centimeter. And with this 1 centimeter depth, we found, using the calculations, we found that the wavelength that we would need should be less than or equal to 2 centimeters. And like I would emphasize all throughout this presentation is that this project has a budget limitation. Our linear stage was, our hardware also has its limitations since we want it to be as cheap as possible, and our linear stage that we have has a limitation of like a maximum period of half a second. So we calculated like the minimum wavelength that we can generate using this linear stage, and using this calculation, we found out that the minimum wavelength we can generate is 78 centimeters, which is definitely not less than or equal to 2 centimeters. So in this calculation, it concludes that with the depth and hardware constraints that we have, we were not able to generate deep water waves. So now we have to transition into generating shallow water wave and see if we can even generate shallow water waves. So for shallow water wave calculations, we used the same relationship. For shallow water waves, we have the ratio between depth over this wavelength should be less than or equal to 0.05, and we found that the minimum wavelength of our wave to be considered as a shallow water wave should be 20 centimeters. And using the wave celerity for a shallow water wave and the dispersion relation, we found that with the maximum period of our stage, the minimum wavelength we can generate is 0.6 meters or 16 centimeters, which is still not greater than or equal to 20 centimeters, but we can generate a 20 centimeter wavelength using our stage, since we can just slower our speed to make a longer wavelength. So yes, so the minimum wavelength that we can generate is going to be 20 centimeters, and with all the calculations, it would have a period of 0.64 seconds. So in this slide right here, it just shows the relationship between our wavelength against the period and the wave height against the period. So it's we can see over here that as we increase our period, our wavelength also increases, but as we increase our period, our wave height decreases. So we need to find that like sweet spot where we can see like a good wave height, and it wouldn't be that much long since we want this project to be as compact as possible. So now that we know what type of wave we want to generate, what type of wave generator it associates with, how we can relate the wave generator to the wave we want to generate, now we have to take into consideration our hardware, which is our linear stage. So the linear stage that is being used in this project is this stepper motor linear stage. So most of the time, people use this like a library to control like stepper motors, and in platform IO they have like a fast axle library or like an axle stepper library, but these libraries uses constant acceleration, and for if you're going to use constant acceleration, you would have basically, if you say you turned it off, you go up to like a constant acceleration, it's just going to stay like that, and you turn it off again and you go on like another constant acceleration. It doesn't really generate a sinusoidal wave, but more of like a box wave, right? So now we have to find a way to be able to generate the sinusoidal wave that we want. So to achieve that, I took the approach to basically relate the sinusoidal wave that we want. So in this graph right here, the y-axis is the wave height, the x-axis is the period, and we basically divided like the periods into sections, into the same time interval sections. So in each of these sections is going to be the same time interval. And this graph right here is just like a simple concept to explain how I approached the project. So in this graph, you can see that the distance from 0 to the first point, and from the first point to the second point, and from the second point to the third point, the distance in between them gets smaller. So that suggests that in each of these sections, there's going to be less steps that you have to take, but it's going to be the same time interval. So what I did was I translated this position of like the sinusoidal wave and translate it into like steps. And I basically created a program code where we would feed in like the amount of steps that it needs to take in each iteration. And in each iteration, it would have like different delay, since it has like different steps in each section, but it still have like the same time interval as the previous section. So that's how we were able to generate that sinusoidal wave. So now that we know what type of wave do we want to generate, the wave generated we're going to use, how we're going to relate the wave generated to the wave, and how we're going to use our linear stage to generate the sinusoidal wave that we have, we're now able to create, we can now start designing and modeling our flume. So this is a CAD model of my project, which gives you guys the overview of like what are the parts and like basically what is in the flume. So over here we have the linear stage that we used. These stuff, like this part right here, is like the saddle where my linear stage sits at. This is like the piston, and in every flume there's always going to be a wave absorber, because if you generate a wave, there's going to be, and like it's going to hit a wall, it's always going to reflect. So if you have like an incoming wave and a reflected wave, and that like adds together and like that creates like a standing wave, which is not like the wave that like the wave height that you want to generate. So to ensure that the wave doesn't reflect back, we have like this wave absorber to help dissipate that reflected wave. And over here is just like a little drawing that I did. It's basically in like the main project itself, it's like a little tile scrub padding to help just also to absorb the wave itself. So in this model, since the minimum wavelength we can generate is 20 centimeters, we gave the flume a dimension of 60 centimeters length to accommodate, like to see at least a few waves in there, and to accommodate the wave absorber at the end. And then since the wave height are significantly small, they're usually on like the millimeters, we gave the flume a height of 5 centimeters, mainly to accommodate like the linear stage and the piston. And then to make the flume as compact as possible and to also not strain our linear stage, we gave the flume a width of 5 centimeters, which is also just enough to where my linear stage can like get in there and like, you know, with like the help of like the saddle to sit on top of it. So that is like the main overview of like the dimensions of like my flume. And now just going into the parts. Of course, we have like the flume itself. Like I said, it's going to be 60 centimeters long, 5 centimeters high, and 5 centimeters wide. And this is actually a photo that was taken during like the construction part. So we use like this jigs right here to ensure that the side pieces would stay in place. And for like the whole length of the flume, it would be the same width. And then next is the wave absorber. So this was like the scrubbing pads that I was talking about to help dissipate the waves. And then we also have this saddle. So this area is basically where my linear stage would sit, and it would just like hold it in place and to stabilize it. And then of course the piston, which is basically our wave generator. So in this piston, you can see this little knob right here. That is a spacer, because if you connect this piston without that spacer with our linear stage, it would basically like hit this like bottom part of the saddle, so it would like create that friction. So to avoid that, we created that I added that little knob right there, which is like a spacer to create that little space in between the saddle and the piston. So going into like the electronics component of the project. So in this diagram, it just basically shows like the connection of all like the electronic components that I used for to make our stepper motor work. So of course, one, we have like our microcontroller, which is going to be connected to, which was connected to my personal computer, where my personal computer which has the program, and it would upload the code into the microcontroller, which would be able to talk to our motor driver. So like our motor driver is like the main controller of our stepper motor. So to be able to control our stepper motor, we need to have our motor driver. And then third is like the power supply. So this external power supply actually supplies the power that will be used by our linear stage. And then we have a capacitor to help stabilize the power that we are feeding through to our stepper motor. And of course, lastly, we have the stepper motor, which in our case is the linear stage. So this is what my project looks put all together. So we have our power supply right here. We have the wave absorber. We have like the linear stage, the piston, and all the electronics component. And here's just like a little snippet of like the final result of my project. So as you can see, we have like few waves in there. And it's getting absorbed by our wave absorber at the end. So just so the conclusions of this project. So I did did some percent error calculation. So I checked if it matches like all the are the observed values meet with like the expected values or like the calculated values. So for our period, we expected a 0.64 seconds. For the observed, we have 0.7 seconds. So that's a percent error of 9%. For the wave height, it was very hard to actually measure this wave height. But I was able to find a software where it provided like a ruler that provides this millimeter calculation, and according to this, the observed is 2.8 millimeters. But that's the amplitude, so we have to multiply it by 2 to create the wave height, and the expected wave height was 6 millimeters, and we have an observed of 5.6 millimeters, and that gives us a percent error of 6.67%. And then for the speed of the wave, we expected our speed to be 31.30 centimeters per second, and with the observed, we got a 30.16 centimeters per second, which yields us a percent error of 3.64%. So all in all, I would say that this project was actually a success, since all of the percent errors are less than 10%, which is actually really great. And now I just want to talk about like the project budget of this project. So here we just have like the linear actuator, the acrylic sheets, and like the acrylic glue. And because most of my parts are actually 3D printed, which I utilized the 3D printers here at our OE lab, and it yields us like a total of $78.82 just for the whole project. So it is very cheap project. It was a very successful project, I would say, and it's also easily replicable since it's like $78, like almost 80 bucks. So yes. So all in all, that was like my projects, and like that was like the conclusion of my project. So I just want to talk about like the skills that I learned and utilized all throughout this project period. So in terms of hard skills, I definitely learned a whole lot more, and I enhanced my CAD modeling skills, circuit analysis, coding, especially in MATLAB and C++. So like MATLAB was for like calculation, like for the wave parameters that I would need, like that I will generate, like the wavelength, the wave height, and of course C++ to control like my stepper motors and all that programming code. Wave theories, of course, it's a wave flume. It dealt with like a lot of wave theories, linear wave maker theories, like deep water, shallow water. And then, of course, stepper motor. Coming into this project, actually, I didn't have any background about stepper motors. I didn't know of them. So diving into this project, I was able to learn like what are stepper motors, how they work, and all that good stuff. In terms of soft skills, I definitely was able to enhance my presentation skills. We were required to do a presentation weekly, and in connection to that, communication and just public speaking, and of course teamwork. Since there are like times where me and my colleagues were having like intertwined tasks, so we had to like figure out how to work things together, so that helped me enhance my teamwork skills. Surprising aspect for this project is definitely a simple concept project can easily turn into a complex multi-step problem. So if you look at like my final video, is literally just a stage going back and forth generating that wave. But if you dive in deeper into that, you would see that how did you control that stepper motor specifically? Like how did you connect all of this stuff? Like what type of waves do you want to generate? So it does turn into like a whole multi-step problem. And lastly, time runs faster than you think. And I think all four of us can attest to this, that all throughout the second semester, we were all just chasing deadlines, and like, because we were running out of time and we need to finish this project by that deadline. So time runs faster than you think, really. So that was it for all of my presentations, and I am very thankful for all of you guys for listening to it, and I'm also very thankful for my professors for guiding me to accomplish this project. And now I'm opening the floor to any questions.
So you mentioned the step value in the code. Do you think if you added more steps, you could reduce that percent error?
So adding steps is more of like so if you add steps, actually it's just like creating like a bigger wave height. So like you're just creating like that, you're just traveling longer distance. So I don't really think that it matters much, in my opinion at least. Because you're just making it longer or higher and all that stuff. So I think for like most of the percent error is more of like personal stuff. So like I maybe have like touched like the stopwatch too long, and also like the stopwatch on like phones are not as precise as we want it to be anyways. So I would believe that that is like the highest contributor on those percent errors.
May I just jump in? Maybe I understood the question a little bit differently. I understood the question if you take more time intervals rather than doing more steps per time interval. Being more precise in how you subdivide your time.
Oh, like divide it? Yeah. I think if we would have like more sections, definitely it would make it more precise, because stepper motors that's why we use like a stepper motor, because we were taking advantage of its like precision on like doing its steps. So I would think that if we created more sections, I would say that we would, yeah. Any other questions?
Can you go to slide number 9?
Yes.
So, so on this slide, for each step, you have for each time interval, you have varying number of steps.
Yes.
But you are following basically the same cycle, like 247, 223, 117. Then
Yes.
negative. So it's basically the same cycle for the crest and the drop.
Yes, because it's like it goes forward and back the same like.
So from the shape of the wave that your flume generated that you showed us in the video, do you think within two crests it followed the same increase in height? For
So
a wave cycle, do you think the increase in water surface elevation for the crest and the decrease in water surface elevation for the trough was occurred equally?
So in terms of like the waves that is generated by my wave flume is definitely it's not like as pretty waves that you think. I mean that I wanted it to be, since if you look closely actually to my project, my piston was like very shaky. that is connected to my linear stage. So it was kind of like generating like little waves in front of like my bigger waves. So like my waves wasn't just like full on like the wave crest. So it has like a big wave crest and like little waves. So I think that contributed to it to not have that the same vertical distance between them. So.
Can you go back a few more steps?
Back?
Yeah, back.
Yes.
Keep going. Okay. So yeah, can you stop on 8?
8.
Yep. So on this one, you said the wavelength is increasing
Yes.
with period,
Yes.
and the wave height is decreasing with period.
Yes.
Why is the wave height not constant? Why is that decreasing?
Because the longer the wavelength, the more of like the wave is horizontally displaced rather than vertically displaced. Is that what you were asking?
So what controls that displacement?
It controls on like how much like the length of my linear stage I move. So if I travel longer in my linear stage, it would be a much higher wave.
So it's your stroke.
Yes, it's my stroke length. Yes, sir.
And you had a constant stroke. You had no way to modify that stroke?
I could. It would be like different steps at that point. So I would have to relate like the steps on like that longer stroke length.
Stage.
Yes.
And one last question.
Yes, sir.
If you can keep going back.
Yes, sir.
Your very first schematic. Yep.
This one?
Shallow water.
Right here.
Okay, so actually that nice wave, linear wave, can be visible in the deep water wave, but do you see how even the schematic shows the shallow water wave?
Yes, sir.
Like a pointy crest,
Yes, sir.
and then our broad. Actually, I would say that's almost like a sketch for a non-linear wave. But I guess waves start becoming non-linear anyway, so you may have no control whatsoever on that. That's why you might have seen such a pronounced crest and not that much pronounced trough, and then there comes your next pronounced crest.
Yes.
And the second following stroke comes in.
Okay.
So that in the end you generate the shallow one.
Yes, sir.
But here it was the same wave height and the water depth.
Yeah.
Didn't see much if you keep it linear.
Yeah.
Any questions?
No more questions?
Yes.
What was your favorite part of your project?
Finishing it, seeing it generate waves for sure. That was my favorite part. Since, like I said, this semester has been like very, very hectic, not just for this class, with other class as well. And finishing it was the best part of it because I was like, I don't want to say that I slacked a little, like after I saw it moving and everything. But I was able to like relax a little bit and like stop, like, like maybe from running, I was able to jog a little, like that type of concept. So, yeah.
What was something that was frustrating and how did you like overcome frustration? Like I like a road area.
Be very careful now.
So in terms of like the project itself, the one that I was like the most frustrating part was definitely controlling that stage into generating like the sinusoidal wave. I remember at one point I did cry. I did cry in front of like all of them because I was so frustrated with it. But yeah, that was probably it. And I think it requires a lot of patience and just resilience. So yeah. Anything else? Anybody else?
Will you give demonstrations of your stage later on? Demonstrations of your stage.
I lost my wave absorber.
What?
The one with like the one with the padding is not there. But I can just use, I can demonstrate it for sure. If y'all want to.
Anything else?
Oh, it's over there. Okay. Yeah, I mean, I can demonstrate it if you want. Something that I didn't expect to happen. Um, Everything. Well, it because it's very much changing. Like what Trevor said earlier, you have to be very flexible in this class because it does changes a lot. So everything is always unexpected. That's all I'm gonna say. It's always like you might expect something, but the outcome is always gonna be unexpected, and you just have to be flexible with it, just like what Trevor said.
Explode. I have a question, but we want to get them to step out so I can ask. What's the advice you have for us coming into PhD?
Advice is before you go into P&D, make sure that you have like a good background of what you want to get into. I suggest to make sure to do some before you, because like y'all are going into it in August, so like make sure that this summer y'all do like a good background research onto the projects that y'all want to do, because I think all of the like my colleagues also would agree to this, that we all took a good amount of time of our projects and design class in just research alone. So if that research part, like if that was shortened a little bit, and like good time management, like once you set your deadlines, keep it and like always hit it, because once you get late on one deadline, it's a domino effect, and it just like frustrates you at the very end. It just keeps on rushing you at the very end. So that's definitely one of my advices. Anybody else? No? Okay, well, thank you, you guys.